Deep neural networks, a subset of machine learning, have become increasingly significant for various applications such as image and speech recognition, autonomous vehicles, and even complex strategy games. These networks are inspired by the human brain's architecture, utilizing layers of neurons to process and analyze different features of input data. The training of deep neural networks involves several key components and processes. At the core, it relies on the concept of layers, consisting of an input layer, multiple hidden layers, and an output layer. Each layer is comprised of neurons, which are interconnected nodes that process data by assigning weights and biases to inputs. Training a deep neural network starts with the initialization of weights, usually set randomly within a specified range. This randomness helps ensure the network does not begin with any inherent biases towards certain solutions. Data flows through the network from the input layer to the output layer, with each neuron applying a mathematical transformation to the data it receives. A crucial part of the training process is the activation function, which introduces non-linearity into the model, enabling it to learn complex patterns. Common activation functions include the sigmoid, hyperbolic tangent, and rectified linear unit, ReLU. One of the most challenging aspects of training a deep neural network is selecting the correct architecture, which includes determining the number of layers and the number of neurons in each layer. The architecture governs the model's capacity to learn from data. A model that is too simple may not capture the underlying patterns, known as underfitting, while an overly complex model might perform well on training data, but poorly on unseen data, known as overfitting. To train a deep neural network, a loss function quantifies how well the neural network's predictions align with the actual results. Common loss functions include mean squared error for regression tasks and cross-entropy for classification tasks. The network's optimization process uses the loss value to adjust the weights through backpropagation, a method that calculates the gradient of the loss function with respect to each weight by the chain rule, systematically updating them in the gradient's direction. Optimization algorithms such as stochastic gradient descent, ADAM, and RMS-prop guide the updates of weights and biases efficiently. These algorithms help in managing the learning rate, a key hyperparameter that determines the step size during the optimization process. Choosing an inappropriate learning rate can lead to slow convergence or even divergence of the training process. Regularization techniques like dropout and batch normalization are employed during training to enhance model generalization. Dropout prevents overfitting by randomly dropping neurons during training, making the model more robust, while batch normalization accelerates training and improves performance by normalizing inputs for each layer. To evaluate a deep neural network's performance, it is critical to use validation data to tune hyperparameters and test the network on a separate test dataset to estimate its efficacy on unseen data. As the field of machine learning evolves, new techniques and methodologies continue to emerge, pushing the boundaries of what deep neural networks can achieve. Understanding and effectively training these models remains pivotal for their application in real-world scenarios, offering solutions that were not possible a few decades ago.